Hello everyone, my name is Alan, and today I'll be going through amino acids and peptides from BioChem Chapter 1 of MCAT. So, this is the start of a series where I try to self-study through teaching and recording these videos, and for your information and also for my own grade review. My MCAT date, I actually did the MCAT one time already. I received a 511 score, and which is satisfactory but not the best at which I want to get competitive with. So I am retaking it this August, I presumably on the 19th. I have not got the test date yet, but I will do so soon. Alright, so let's get right into it. This is amino acids and peptides from chapter 1 of BioChem. So the AAMC specifically says you want 20 protein-genic amino acids and human genome code because there are other amino acids such as GABA and something, erythro or something. However, those may not actually code for an actual amino acid or actual protein. However, they still function very well. But AAMC specifically asked for these ones, so we're going to go through them together. For a general amino acid structure, you have your amino group right over here, and that is your N and bonded to the 2H, and we refer to this as the N terminus because when we have a polypeptide chain, we start with this side and then we end with the other side, the carboxyl group. Carboxyl group, if you know from chemistry, is like a carboxylic acid, hence the name. Amino, you have your little amino group over here. So going from amino group, which is N, to carboxyl group, which is C. C for carboxyl, N for the nitrogen here. And also you have your H bonded to just a central C atom here. This H will always constantly be here, just serve as a hydrogen atom here. And lastly, you have your side chain on the top, which refer to R group for now because it can be any of these depending on which amino acid it is. So starting from a nonpolar group, we have glycine. Glycine is the very basic, not basic as in that form, but the simplest form of amino acid, which the R group consists only of H, the hydrogen atom. Now, with that being said, there's a special rule here where all amino acids we find here are chiral. If you don't know what chiral means, if you hold out your hand, you can see that your left hand and right hand, they cannot overlap each other because your thumb is on the opposite sides. So there's chirality to it. So that means all of these have a specific turning when exposed to polarized light and spin in a only general direction. So your left hand is unique to your right hand. So glycine is the only exception because there's two H atoms bonded to the central, so there's no right hand or left hand to it. It's basically on the same orientation no matter what. So all amino acids here are chiral except for glycine, as well as there's S. S, which is a specific orientation of what's it called? I don't know what S stands for, but S except for cysteine, because cysteine right over here is specifically R oriented. So there's S and R orientation, chirality. You just need to know everything is S except for cysteine. All I'm gonna use black. All chiral except glycine, and all S configuration, that's right, configuration, except cysteine. Great, and cysteine is found right over here. Alright, let's go through the nonpolar groups together. We have glycine, which has a single atom, H atom to it. Alanine has a simple C atom first. Valine, you have 1, 2, 3, 3 carbon atom in like this Y shape. Leucine, you add another to the very end tip to here, so it's 1, 2, 3, 4. Isoleucine, if you're seeing iso, you can see isomer because you simply use stereo isomer and move that carbon atom to right to shift. Whoop. There you go. So still 1, 2, 3, 4 carbon atoms out, but it's moved a little bit. Methionine, oh yeah, it has not an M, sorry for confusion, but instead it has an S bond here. 1, 2, 3, 4. That's right, there's a sulfur atom in there. 1, 2, 3, 4 all together. 1 carbon, 1 S, 1 carbon, 1 carbon. Good. And you have your proline, which is here. And proline is special because it has a loop goes attached to it, linking all the way from the side chain, loop around to the amino group. Let me just double check that methionine has a 1, 2, 3, 4. That's right, I'm missing one additional one here. 1, 2, 3, 4. Good. So 1 carbon, 1 S, 1 carbon, 1 carbon. Great. Now we have our polar group. Polar group are the ones that have additional they can participate in hydrogen bonding, right? Non-polar ones don't have any hydrogens attached to them, and these ones are able to participate in hydrogen bonding or bonding of some sorts, right? Polar bonds. If you learn in chemistry, you'll see that these all have C ending to it, C ending to them, or they can't participate in hydrogen bonding because there's no additional atom for electronegativity participation. Glycine has an H, right, but there's no electronegative atom for it to bind to. Methionine does have an S, but it doesn't have an H group for it to participate on self interactions. Polar groups, we have serine as a start. It has an OH, the hydroxyl group at the very end, in addition to a C carbon atom bonded to it. Threonine is similar, but 1 additional carbon attached to it. Cysteine, very similar as well. However, it has a SH at the very end instead of the O for serine. You can see how this differs because cysteine, the sulfur atom, is bigger and less electronegative than oxygen, right? So it's a little bit more prone to oxidation. If you know oxidation, lose electron, so it's a little bit easier to lose electron for sulfur because O has higher electronegativity, so it holds onto the electrons a little bit tighter. For the asparagine and glutamine, I remember them collectively using in to know that there's an N to them, substituted for the carboxylic acid, kind of like at the end. So I imagine them to have a carboxylic acid at the very end. You can think there was an OH, but it got replaced with the NH2, right? So this might be counterintuitive because you think everything here is OH, but except for asparagine and glutamine, which they have N instead. But they can still participate in their self interactions because the H here, hydrogens, can bond to the O in the carbonyl oxygen. Next, we have the nonpolar one. Not the nonpolar, the aromatic. Goodness gracious. Aromatic. There you go. Starting with tryptophan. I think tryptophan as an elephant because it's so huge, right? You have your entire ring, aromatic ring around to it with the little 1, 2, 3, 4, 5, and this is an aromatic chain with an additional C attached to it. I just remember by just drawing over and over again. It's just like the biggest one in terms of number of rings. It has 2 rings. Phenylalanine is just attached to benzene ring with a C. And tyrosine is the same thing as phenylalanine but plus an hydroxyl group at the very end. Right, a special thing about aromatic compounds is that they can either be nonpolar or polar, depending on what they are. Tryptophan, you can see that there's no H particular, right, attached to them, evidently, because they're all kind of just bonded to the C. Same thing with phenylalanine. So these two will be grouped under nonpolar. However, tyrosine, due to this OH group, it can participate in hydrogen bonding with the H and the O itself, so it will be grouped under polar. And we have our positively and negatively charged groups. Positively charged consists of three. You have your arginine, lysine, and histidine. With arginine, you have your triplet of N's. You have your N up here with NH, and also NH2 with the NH bonded to it. So 1, 2, 3 carbons first leading out from the R group and then bonded to them. Nothing special about arginine, it's just that it has like a triple essential about N, and I'll explain why it's positive, what positively and negatively charged terms is in the next little bit. You have your lysine. Lysine is, I think of it as in lying down to remember it, because it's like stick, lying down. There's no kinks going up or down. And you have your histidine. I think of it as a house sitting because it looks like a house with the two walls signifying the double bonds, and your N going up and your N going to the left bond side. And it just jots out from the R group. Your negatively charged have your carboxylic acid here pretty much, and linked to one more C, and that's your aspartic acid, and your glutamic acid, basically the same thing but plus one more carbon chain leading out. You notice how aspartic acid and asparagine have similar names. That's because I referred to earlier aspartic acid. If you know the term ic acid, that's the suffix for carboxylic acid. So you can very much remember that aspartic acid has the OH group, but asparagine turned that OH group into the amino group. Same thing with glutamic acid versus glutamine. Look at the amine, asparagine. Very easy to remember. Alright, so that's pretty much it for amino acids and peptides. Now moving on, I will be teaching you the positive charge and negative charge aspects and why they matter. See you in the next video.